for part 1 in our chapter 12 in our statistics class, Psych 218A. So today we're going to start chapter 12 on the introduction to ANOVA, or analysis of variance. So as you can see, I got my 1/4 of the screen with me talking to you face to face, and then the rest of it showing you the lecture slide. So we're going to go through the lecture, or at least part 1 out of 5, in about 20 to 30 minutes. I'm going to split the lecture into small chunks, so then you can watch these on a sort of day-to-day basis. You can watch 2 per day or even 3 per day if you're feeling up to it. So instead of doing whole 3 hours, we're going to do half an hour chunks. Let's try this. So here we go. At this time, I would encourage you to watch this on a laptop and not on a phone. Anything that is 10 inches or more in terms of screen size, so you can really see the lecture slides. If you happen to be watching on a phone, do your best to listen in and switch over to a computer the next time. Do take notes as you go and practice. The first one is more conceptual, so do take a moment to think about what's being said and write down what you learn. Okay, so let's go. ANOVA. Hello! So this is the whiteboard that we can use, and sometimes I would use this to write stuff. That's one way for me to communicate with you if I need to work with whole formulas and sheets. The other way I can communicate with you on the screen is I'll take a screenshot and I would start writing on it. So for example, ANOVA stands for Analysis of Variance, right here. And the idea is that when we compare more than 2 groups, so it could be 3, 4, 5, or even 10 groups, we are going to need another tool other than z-test or t-test to figure out if the samples are different from the populations that they're drawn. Okay? So here are the 5 outcomes we're going to do for our lecture this week. There are 5 parts, and I'm going to go through part 1 today, hopefully in the next 20 to 30 minutes. So here are the parts. Part 1, we have the logic and purpose, or the purpose of logic of ANOVA. Okay, analysis of variance. We will go through the reason why we need a tool like ANOVA to compare more than 2 groups. So again, 3, 4, 5, or more. The next section will cover how to use ANOVA and how we can use it for single factor studies. And we'll explain the term factors and levels as well. So stay tuned for that. Part 3, we're going to describe when and why we want to do post hoc test. Post hoc means after the fact, and so after we determine through ANOVA whether multiple groups are same or different, and we decide to say, yes, there probably is a relationship between them, we would do after the fact or post hoc test to see what kind of differences we have. Number 4, we're going to look at Tukey's HSD, or honestly significant difference, or the Sheffe test, as 2 sample post hoc tests. And finally, the last thing we're going to do with ANOVA is look at rho squared. This is a Greek letter for rho. It's the Greek version of R. And again, we're using this to measure effect size, or in this case, if you remember R squared, R squared, again, that one is percentage or proportion of variance explained. Okay, so we're going to do the same with ANOVA, but it's going to be called rho squared. Okay, so those are the 5 parts, and we're going to focus on part 1 today. So today we're doing part 1 today. Okay? The math tools you need, I'll go over these in brief. Because ANOVA is the analysis of variance, you will need to recall and practice Chapter 4, the parts on variability. This includes the sum of squares, or SS. Now you may remember how we got this formula and what we need to do. So something like this, right? And that's add them all up. Then we need to get variance, or sample variance, okay? And then we need to also remember, because we're dealing with samples, we're going to need to use degrees of freedom to account for sample bias. So again, degrees of freedom is n minus 1. Another tool you're going to need is the logic of hypothesis testing. So remember those steps, those 5 or 4 steps. Okay, so remember those steps. Take a moment to review them, what step 1 is, step 2, step 3, step 4, and step 5. The first 4 steps are the most important, and the last 5th step is for you to write words in English, whether you decide to reject or fail to reject the null and what that means. Finally, we're going to work with independent samples, t-statistics, in 2 ways. One, we're going to use it as the skills we already use, and we're going to use it today to explain why we can't use t-tests for multiple pair comparisons. So we can't compare free groups or free samples or more using t-tests that only compare 2 things at once. Okay, so the next couple of slides may seem out of order, but let me walk you through it as we introduce ANOVA, or analysis of variance. With ANOVA, as you know by now, it is short for analysis of variance. Okay, and we use it to see if there are differences between 2 or more treatment groups, and we specifically mean more than 2. As we go through part 1, we'll explain why we use ANOVA for 3 or more differences. Okay? And we're going to use sample data as a way to show this. Okay? Alright, the next step we're going to do is show why ANOVA has a clear advantage over the t-test. And one more time in this slide, we're going to say that ANOVA is very useful to compare more than 2 treatments at the same time, and we're going to prevent something called cumulative experiment-wise alpha. Okay? So take a moment to think what alpha means. So alpha is the probability of a type 1 error in a given experiment. And if we do more than one experiment or do more than one pairwise comparison, the alphas are going to add up, which means the probability of a type 1 error is going to add up also. That's one clear advantage. I'll say it now, just for you to think about it, and as we go through the next few slides, it will come back to you and make more sense as we look at it in the slide itself. Okay? Here is a typical example of a situation where we probably would need to use ANOVA. Alright, so as you can see and count, there are 3 circles with 3 samples from 3 populations. So you can see here mean 1 or mu1, mu2, and mu3. From each population, we grab a sample, and you can see here sample 1 with its own sample size, its own mean, and its own sum of squares. Sample 2 has the same sample size, but a different mean and a different sum of squares. And sample 3 has yet the same sample size, but remember, these are all from its own unique population. Sample 3 from population 3, and it has mean of its own and a standard deviation or sample sum of squares on its own. So n here for sample 1 could read as n1, M here could read as M2, and SS here could read as SS1. So if I do this quickly, you can see that these are its own sample data or sample statistics. So the challenge here is, how are we going to compare them? Do we use t-test and make multiple t comparisons, or do we use ANOVA that we're going to learn today? This lecture shows you an advantage of using ANOVA. You don't necessarily have to use ANOVA every time, especially if you're only doing 2 samples, but it is good to know why we need to use it. Here are some terms and concepts in ANOVA that we need to use. And today we're going to start with 3. The first one is the factor. The factor is the independent variable, so IV, if you remember from your research methods class at Alexander College, that's Psych 217. These factors are independent variables that we measure for the group. And if you think about it, each group, while they are in different groups, we are measuring the same thing. So if you go back to the previous slide in your Google Slides and look at those 3 circles again, you will see that yes, there are 3 means, 3 sample means, some 3 populations, but we're going to ask the same question. Hey, it could be about body temperature. What is the body temperature on average for sample 1? What is the body temperature on average for sample 2? What is the body temperature on average for sample 3? And so asking that question, seeking that independent variable or measuring it, that's the factor. Okay, so here is the factor or independent variable. Within the factor, there are levels. Those, as the slide says, are individual conditions or values that make up a factor. So, again, this may make you think about measurements or scales. So, the levels could be discrete, it could be continuous, it could be nominal, ordinal, interval, or ratio. But these are levels to the factor or measurements in the independent variable. Taken together, when you have a factor that you're going to measure for different groups and different levels within which you measure each group in that factor, we are making a factorial design. You can make a factorial design for more than one factor. So when you combine factors, we have a factorial design with levels. Right now it's just words. I'm going to show you what that looks like in the next slide. Here is a sample of a 2-factor research design. I will show you what the factors are. And before you do, take a moment to pause the video and see if you can figure out the factors and levels by yourself. Can you do it? Okay, here we go. Let's take a look. There are factors and levels, so we need to know what these are. See if you can figure it out. So, factor, here is the first one. Therapy technique, something we're measuring. An independent variable. The other factor is time. So this one has 2 factors. As you can see here, this is factor 1. And here is factor 2. Therapy technique and time. Within each factor, there are levels. For factor 1, there is therapy 1. And for factor 2, there is therapy 2. So here is factor 1, level 1. So for factor 1, level 1 is therapy 1. And therapy 2 here is factor 1, level 2. See if you can find the levels for factor 2. They are before therapy, so here's factor 2, level 1. After therapy, factor 2, level 2. And 6 months after therapy, factor 2, level free. With each factor and level, you can do a measurement. So you can see here for therapy 1, group 1, before therapy, there is this measurement. Scores for group 1 measured before therapy 1. In the same factor, there are 2 more measurements. After therapy for group 1 and 6 months after therapy for group 1. The same can be said for factor 1, level 2. So here is group 2, and they have 3 measurements. 1 measured before the therapy for group 2, 2 measured after therapy for group 2, and 3 measured 6 months after therapy 2 for group 2. So here you can see a 2-factor research design, 2 factors, therapy technique and time, with different levels and a measurement for each interaction between the factors and levels. Here you can see 2 factors. For factor 1, there are 2 levels. For factor 2, there are 3 levels. And if you multiply the levels, 2 times 3, you get 6. So there are 6 measurements outlined in this grid. So with so many measurements, we're going to need to figure out a way to write the null hypothesis as well as the alternative hypothesis. Whether we are going to test there is a difference between the means or there is no difference between the means. And later on, we're going to ask whether there is a relationship between the means in terms of their variance or there is no relationship. For now, let's look at it as means and figure out how we're going to write the null hypothesis for different means, more than 2, in this case 3. So take a look here. The null hypothesis, as you know, means no difference, okay? Alternative hypothesis means yes difference. Okay. So here, as you can see, if we say all the population means are equal, then that's the null hypothesis. In the words in the slide here, this means it says, yeah, the means of the groups don't differ from each other. It's really as simple as that. Notice before we only work with, as many as 2 population means. This time we're going to add 1 more or more. So it could be 3 means, 4 means, 5 means, or 10 if you wanted to. But we're going to see where we might run into some trouble when we compare 3 or more means. Here is the alternative hypothesis for multiple mean comparisons. So what we say, and we use words here rather than symbols, the word version goes like this. This is the more plain English version. We say there is at least one mean difference among the populations. So even shorter than that, we just say not null or not H naught. So again, H1 or HA is your alternative hypothesis. Your H naught or H0, if you read it like that, it should say not. That's how we say it in our statistics circle. You may notice, again, rewriting the null hypothesis here, all the means are equal. So if we were to write the alternative hypothesis with symbols, we might have to write something like this, and there are different ways of writing it. Here is the first obvious way, saying none of them are the same. None of them are equal to each other. But take a moment and think if there are other possibilities to write the alternative hypothesis, which makes it also not the null. Can you figure it out? Well, here are some examples. If you are thinking, well, I only need to say one of them is different, then you're absolutely right. So it could be, for example, that mu1 is not equal to mu2, right? But mu1 could be equal to mu3. Well, as long as one of them isn't the same, that is still not null, isn't it? So we can go mu2 is not equal to mu3, but mu2 could be equal to mu1. Again, you can work out the possibilities with this, which is why it's more common to write with words to say there is at least one mean difference among the populations. And as we think about this, this is why we have the caution point here for our slide. How many ways can the null or the null hypothesis be wrong? Well, here's the first way. Again, reviewing what we thought so far. First, all the means are different from every other mean. So that's, scenario 1 over here, or it's called A. Scenario B, as we talked about in symbols, is that some means are not different from the others, but some means do differ. So here, this bit is scenario B. Now we're going to run into some problems because when we write our alternative hypothesis, we are almost by default required to run multiple comparisons, especially if you consider the possibilities of which mean is different from which one. So let's keep going. Before we go into the disadvantages of doing pairwise comparisons using T, we're going to show you what ANOVA is using the F ratio. This is not the same as your T statistic or your Z statistic because we're measuring something else here. We're not comparing means. We are looking at the proportion of variances. Let me show you what we mean. F ratio. So it's a ratio, so it has a numerator at the top. As you can see here, this part is the numerator or the top bit of your fraction. And the bottom bit is your denominator, the bottom bit of your fraction. As you know from fractions, the bigger the numerator, the larger the ratio. And so at this point, I'd like to say that the closer the F ratio is to 1, the more percentage of the variance is going to be, explained by between group variance or the treatment effect between groups. For now, let's just read what the F ratio is. The top part, the numerator, is the variances between sample means. So we're looking at things like, I'm not going to use mu anymore. I'm going to use sigma. Okay, sigma squared 1. Okay, I'm going to use comma, sigma squared 2, and sigma squared 3. Those are the things we're going to look at here. The denominator is the variance or differences expected with no treatment effect. Another way of saying this, within sample means. One way to look at this, or one way to reword this, is individual differences within the groups. So, for example, using body temperature as an example, there may be 3 different populations with slightly higher and lower averages in body temperature. Maybe they live in, warmer and colder climates, although that technically doesn't change because our bodies regulate our own body temperature. Maybe this applies to more cold-blooded creatures, but I digress. Like lizards. I digress. Still, there are differences between groups that we can probably expect, especially if we do certain changes with conditions. Think back to your factorial design. And there are differences in body temperature within groups. Just like everybody's body temperature is different in some way. So I paused this video twice now, and I'm going to move on to the next part. So remember, we're going to examine the variances between groups, between means, over the variances within groups, or the overall variance, or individual differences.